Thanks, Sandy. Yeah, so I'll talk about transfer learning and then both sort of about the specific setting of transfer learning which we look at, which is domain adaptation, as well as what the problems are with current algorithms and how we try to work around these problems. There will be quite some machine learning, no equations, but I will have sort of architecture schematics, so please hang in there, end of day. So to start, what transfer learning is, and transfer learning more broadly is where you try to repurpose a model that you train for one task to use for another task, right? And this can be if you are a mobile phone provider and you have information in one region but not in another region. This can be data sets across hospitals. As Sandy says, this is a super general problem. And we look at it in a sort of a controlled setting, which is domain adaptation, where you have two data sets, a source and a target. And on the source data set, you have both sort of the raw data as well as the labels, so as well as the outcome, the thing you have to predict. And on the target data set, you only have the raw data, but not what you want to predict. And generally, especially deep learning algorithms, so sort of the simpler your algorithm is, the better it can transfer knowledge. And these deep learning algorithms, so what we see a lot in sort of the paradigm now, are generally very brittle. So they sort of over-optimize on one task, but because they don't have an intuitive understanding of physics, an intuitive understanding of the world, they learn in a very different way, and they over-optimize on whatever they're trying to learn. And they're very good at that, but that comes with some problems. So I thought that was the pointer, wait. So generally, if you learn objects on a white background, and this is what your computer vision algorithm, whatever the deep learning architecture is you use for that, and you know how to classify objects on a white background, and you're trying to transfer that knowledge to these objects in the wild, right? So here it's bicycles in an office. Then if your algorithm is trained to do this, it will barely do better than random on this task, right? So it will do very, very badly. So how can you still transfer knowledge between these tasks? And this is a problem you also see in natural language processing, where you see also how critical it is to develop these algorithms, because here you want to do sentiment prediction. So you have a piece of text and you want to know, is that piece of text positive or negative? And loads of companies are interested in tracking sentiment on Twitter, but where most of the data is on Amazon, because who labels these Amazon reviews? The people themselves, right? They, for free, give us millions and millions and millions of I sound a bit like Donald Trump now. Give us millions and millions of, yeah, and it's billions and billions is Trump. But they give us loads, maybe that's a better way of saying it, they give us loads of sort of free labeled examples. But this also goes beyond sort of the typical machine learning domains of NLP and computer vision, but also if you have, for example, a classifier that can predict poverty in Nigeria, then there's a related task of predicting poverty in Uganda. So let's say, for example, from census or from satellite images. And then to transfer that knowledge, you have to work with an algorithm like this. So first, let's go of what is now sort of the state of the art and which is the fundament of most of the algorithms that people are working with now. And that is generative adversarial networks, or GANs. And I'm not sure if, or sort of how many of you have heard of this, but this is, I think, and I think a lot of people agree with me, the most exciting thing that happened within machine learning in the last 5 years. Sort of, we're now on top of the hype, and we also see applications in industry, but this is in research. A lot of the research was focused around GANs in recent years. And how this works, very briefly, is that you have a generator, and this generator is a neural network. So anytime, for those of you who see a neural network for the first time, every time you see someone talking and you see these weird layers, it's always some neural network architecture. And here you put in random noise in this generator, and this random noise is transformed to an image. And you start with, obviously, if you put random in, you get random out, so the outcome is a random image. But now there is an extra network, which is a discriminator. And this discriminator, all it does is saying it gets images in, and it has to say this is a real image or this is a fake image. And at the same time, you have a training set of real images, which are in this case handwritten digits. And what happens over time is that the discriminator gets better at discriminating real from fake, and the generator is trained in a way that it has to fool the discriminator. So the generator gets better and better and better over time at generating fake images. And then you think, okay, what's the purpose of generating fake handwritten digits? But if you start at round 0, first you get noise out, but quite quickly, round 1,000, round 2,000, and for some of them, I can already not see anymore that they're fake, right? They seem like real handwritten digits. And also, if you look at actual people's faces, these faces look like they could be, I don't know, your family or friends, but these are people that never really existed, right? So these are people that are outputted by these generators, which are trained in this exact way, but then the training set was a data set of images. So now, how can we use this to do domain adaptation? So this is probably the most difficult looking slide in my presentation, so follow me. And from here on, things are only getting better. So this network has different parts. It has a feature extractor, and this feature extractor you should just see, and you put an input in, and this input can be an image or a piece of text, and it transforms it to a vector. And a vector is just a sequence of numbers, right? So you, for example, you put a megabyte pixel in, and it puts, I don't know, 512 or 1,000 numbers out on this side. And then from here, it goes two ways. And there are two networks, and they both use the same vector, so the same sequence of numbers. And one part of the network is trying to predict a class label. So this, for example, positive or negative sentiment, or is it a bicycle or a unicycle? And the other one is trying to predict the domain. So is it coming from this white background data set, or is it coming from Amazon or Twitter? And if you train this, you have access to a lot of Amazon reviews, so this network will do very well, right? An absolute great read and delivered on time. So this is obviously an Amazon review and not a tweet, right? So we got that right, and it's positive, right? So you think perfect. But now the problem comes if we start to use this on Twitter. What we do now is that the trick is, and that's why it looks like the GANs, the generative adversarial network, is that we train this part of the network to fool this domain classifier. So we're trying to still do well on predicting sentiment, but deliberately not do well on this domain classifier. And now you might think, okay, why are we doing this? If we now look at Twitter, at Justin Bieber, you are the best, we will know it's positive, right? But because we've never seen Justin Bieber in the Amazon data set, we've never seen hashtag I love you so much, we're not very confident, right? And further, we know that this is coming from Twitter. But now, when we train this part of the network to fool this domain classifier, we automatically get a representation here of that piece of text or image or whatever you put in, which is invariant of the domain. So you learn knowledge in a way that's much more general, because you try to learn knowledge in a way that doesn't depend on the domain, that doesn't allow this part of the network to know the domain. So you immediately see that our confidence, and therefore also our accuracy over the whole data set, spikes up, right? So we do much, much better than we did before. But there's a problem here, and that's why we started also working on this, is that what these researchers say, they live in this sort of perfect, I had a bottle of water, I think. Oh, maybe it's there, so. But these researchers sort of live in a perfect world, and they say, first, we start working on this problem because we work on where you don't have labels. But before we do this, we first take these data sets and create sort of these artificial worlds where everything is 50% positive and 50% negative. However, the real world doesn't look like this, right? So their algorithm works perfectly in their papers, but as soon as you start really working on problems, poverty is not a 50% problem. If you transfer knowledge, these distributions are not the same. And you see this also with Amazon and Twitter. Amazon is majority positive, Twitter is majority negative, which is maybe says something bad about society overall, but that's a different story. So now when we start to train in the same way, that we're trying to make the classifier in a way that it can't predict domain, automatically because the domain can use whether it's positive or negative, because if it's positive, it just always says Amazon. If it's negative, it always says Twitter. So if you try to fool this guy, the domain classifier, you automatically also fool this guy, right? So you can't fool one and not the other. So this network, despite a lot of papers coming after it and having a lot of success in the research community, never really caught on because it just doesn't work for these real-world data sets. Okay, so that was the problem part. Now we get the solution. So our solution, we start again with a simple network, right? So again, this is just a neural network with some layers. It's a lot more complicated on the inside than it looks here. So you have all these special networks for text or for vision. But this is sort of the easiest representation. And you have an Amazon review coming in and a positive or a negative sentiment coming out. But now we do something extra where we have what they say a generative network. So we take this label, so positive or negative, and use this to recreate this piece of text. So for example, we use the previous word in the next word, and we use the sentiment. So first we take this whole review and say, oh, it's positive. And now word for word, we try to use the word absolute and the word read to predict the word great. And if this review is positive, then great will be more likely. If negative, then it will be an absolute shitty read or bad read. So doing this, by recreating this word, you learn also more about the sentiment. And you can do this also for other things, for humor, for sarcasm. So it works much more generally. And how does this work in more detail? If we start and we only trained on Amazon and we get this tweet, @John, you are my sweetie pie, hashtag I love you so much. I never heard of this if you live in a world which only exists of Amazon reviews, right? So it has no clue what to do with this and it will say neutral, right? Random, it will say positive or negative, but it has no idea. And now it gets the following tweet, @Marianne, you were a sweetie pie yesterday, love you. Now from love, because it knows this from Amazon, it will know it's positive. And because it's recreating the input word by word, it will learn that all these words are slightly more positive. Right? So now it will learn, because sweetie pie is always co-located with positive words, it will learn slowly that sweetie pie is a positive word. Sorry for choosing these words, but I needed words that only occur in Twitter and not in Amazon. So the next time it sees the same tweet again, suddenly it will know that the whole tweet is positive. So we learned knowledge that we never knew in the beginning without ever using labels, right? And we do this in a completely different way than we saw before, so we don't run into the same issues. So now if we compare the actual accuracies, or here we look at AUC, which is sort of an accuracy, but then for unbalanced data, that our method sometimes does better, sometimes does worse, and on average it sort of does the same, right? So you think, why did we even start with this? But now if we look at unbalanced data, you see that it does much, much better than the network that we're benchmarking against and the network that most of the researchers are building on, right? So we know that there's a need for domain adaptation because there are some domains where we have massive amounts of labeled data, while other domains where we have no labeled data. We know that we need methods that work in the real world. So that's why we believe that we actually, our network and our method is a really strong contribution. But there is obviously still some future work. So this now works for text, but how are we going to do this generative part for vision? And we have quite a lot of ideas how we can do this with higher level features and special networks. And there are ways that we can do this for vision and for tabular data, but we still have to implement those. The second thing that I'm very excited about, because these two sort of methods work very complementary, right? They work in very different ways and achieve in the end a similar result. So we believe that if we put it in combination, that we can make a network that is even better than both networks independently. And then the last thing is semi-supervised learning, which sounds very technical, but is hugely important because that's the setting where if you have massive data sets, but you only have the labels for a few of those data points, how can you then propagate that knowledge throughout the data set? But also on the application, I think one thing you've seen today is that we both try to make theoretical contributions in the group as really looking at applications is, for example, country to country or region to region, right? If you have knowledge, social science knowledge that you get from big data in the US, how can you transfer that knowledge to, for example, Mexico? Or in healthcare, if you have one electronic health record system or one X-ray machine, how can you transfer that to another electronic health record system or another machine? And one thing that I'm personally very excited about and that we're planning to work on is the combination with federated learning. So Abdurrahman, I think, told you guys early on the day about federated learning, but federated learning really looks at the case where all these devices or all these different stakeholders have a common goal, right? They all have sort of different data, but they're all looking to achieve sort of the same accuracy on the same type of model. But obviously, this is often not how banks or healthcare systems work, right? Everyone has a slightly different goal or a slightly different data characteristics. So in the end, you need a system, you need sort of an ecosystem where you have both federated learning, where you have transfer learning, where you have auditability and blockchain, what Thomas will talk about. So that's one thing that we're very excited about, is to try to combine these different methods into one more holistic system. Cool, thanks.